lot of computational power. Okay, so yeah, so like if there are like some questions, I can like dig deeper like towards the end. But yeah, so that's like very large, I would say, umbrella under which we do a lot of computational activities which are helping us to like improve the livelihood of people across the world. Okay. Yeah. So let's move on to next topic, which I think like most of you are in a sense aware, but I thought like okay, so let's see it. So I think like everybody has seen this kind of vehicles, right? So like so if you are a company who is like manufacturing this vehicle, okay, if you look at this vehicle, okay, the design is optimized for space and certain criteria, right? But if you look at the aerodynamic shape of this particular vehicle, and if you try to see like what kind of like average or mileage this vehicle will get, probably will not get like good mileage, because like if you see this front side, okay, when this vehicle is moving, like there will be a lot of air resistance to this vehicle, and so the mileage may not be so great, right? So now if I look at a vehicle like this, right? So here, if you see, like this aerodynamic shape, which allows the vehicle to run at like high speed. At the same time, the air resistance is also very much optimized. So probably assuming everything is same about these two vehicles, okay, still probably this vehicle will be able to get a better mileage than the previous vehicle. Okay, simply because of the like less amount of air resistance. So these companies, these organizations actually go and do this kind of simulations to design these vehicles so that they are aerodynamically like nice, and you get a higher mileage. At the same time, like there are certain patterns. So for example, like some of you might be aware of like older generation of like some of the like vehicles, the way they looked, and with facelift they modify something else, right? So minor changes. Okay, so one is there are some aesthetic changes, and another thing is like okay, so certain times when they realize okay, certain areas lot of dust is getting collected and so on. So what they do is they realize like based on the customer feedback, hey, this is what happens. And in fact it happened with one of the vehicle. Okay, I cannot name it, but okay, the company had to do like simulation like multiple times to like redesign the rear part of the vehicle, simply because like there was a lot of dust catching because of the aerodynamic shape of the vehicle. Okay, so when the vehicle is moving, like all the air is like passing from like all the sides, but at the same time it's creating certain vortices like around the vehicle. Okay, especially at the back side of the vehicle, which was like accumulating a lot of the dust, right? So all this simulation nowadays most of the companies do, and before you actually see the first prototype built within even the company, okay, they have done like a lot of like online design. At the same time, another point I think like which I can bring up here itself is the crash simulation. Nowadays people are more concerned about the global NCAP like rating, like 5-star safety of a car, and so on. So all those things you can actually build a prototype and then crash it, or you can design this thing in computer and you can actually run a simulation to see how that crash will affect the vehicle and so on. So based on like multiple simulations, you can improve the design, okay, or structure of the vehicle, so that you don't have to actually prepare the prototype and then physically crash it, okay, because it's going to like cost you something, right? So people do those kind of things. Also like another point, because like I didn't mention it. Okay, nowadays like many of you might already have vehicles which has a ADAS built in, right? So ADAS is like advanced driver assistance system. So what it does is essentially it captures like surrounding via visual or radar based like thing, and it will figure out okay, what's happening, and accordingly like it will help you as a driver to like safely navigate your vehicle. Okay, so at least like in US, like there are some autopilot options available with Tesla and all, which we do not have here. and there are some robot taxis which are already running in California and some places in US where there is no driver and a vehicle moves on its own, okay, without even remote assistance. Okay, again, those are pilot vehicles, but actually you can take a ride in those vehicles as a Ola Uber kind of stuff, whatever is available there. Okay, and you can experience it, which actually kind of gets all the data from the surrounding and actually moves the vehicle based on the obstacles available and path available and so on. So in fact, there is a very interesting documentary available, I think, on the YouTube. Okay, so DARPA, as everybody probably know, had this challenge for autonomous vehicles for military purpose, of course. So that time, they had announced $1 million prize for that autonomous vehicle contest, and one of the vehicle from Stanford University, they won the challenge. So in fact, if you look at that documentary and related material, they had a GPU cluster installed inside that particular vehicle just to sense the surrounding and build awareness of what's there around the vehicle, because the vehicle's speed depends on how quickly you can collect the sensor data, okay, which can be very fast, but making sense out of the data and building the environmental picture, okay, in virtual is the key, and how quickly you can process it, it determines how fast your vehicle can go. If I'm able to figure out that there is an obstacle 10 meters ahead, okay, and if it takes 1 second to figure it out, and if my vehicle speed is let's say 60 kilometers per hour, I'm going to hit it, okay, and probably I will realize it after hitting that obstacle. Okay, so the point is, if I'm able to predict it within few milliseconds or whatever, okay, probably I might be able to apply the brakes, otherwise my system is going to just crash, right? My vehicle is just going to crash. So all these things essentially use some kind of computing power, and these kind of things for like simple things such as lane departure and those things probably might be easy. Okay, still they use some kind of embedded GPUs and so on, but when you want to do fully autonomous kind of things, you cannot do it with simple desktop or even server grade kind of processor. You need a very sophisticated computer which has lots of computational power. So in a sense, it's a mini supercomputer installed in each and every vehicle, which will actually do all these things, right? So this is where things are moving, right? And that's what probably if you follow Tesla, okay, so Tesla has built their own supercomputer. At the same time, they are building their own supercomputing kind of chip, which will go into their car, right? So if you are interested in knowing more about it, you can just
Sir, your mic is on mute.
okay. Oh, by mistake, somebody mute me or something.
Yes,
I
yes,
don't know.
sir.
Yes, sir, by mistake.
Okay, okay, sorry. So, okay, so I don't know what was the last statement I made, but what I was trying to say was now the cars or the vehicle themselves are trying to become supercomputer on wheels. Okay, and that's how you can go towards the actual autonomous vehicles, right? And if you see a lot of the traditional vehicle manufacturers, especially Ford and those kind of companies, they are struggling because the new definition of a vehicle is not mechanical vehicle in a sense, you have engine, you have four wheels and all the systems, but it's a software defined vehicle. Okay, so the software is the one which drives the vehicle, and which has some hardware component to it, but the heart of the vehicle is not the hardware components but the software part, of course including all the computing systems, but the physical hardware components such as all the drivetrains, engine and sitting arrangement and everything, that that's a secondary citizen as comparing to the computational power and computing capabilities and the network. In fact, if you look at most of the modern vehicles, it's they have their own network on the car because there are so many different chips talking to each other uh, in live. And I'm not talking about some companies in US. It's already here in India, and most of our vehicles, if you buy vehicle today, most of your vehicle, we have hundreds of different chips. So in fact, you must have seen this news during the COVID time that most of these car manufacturers, they have manufactured the car, and those cars are sitting in their stockyards, and they are not able to sell it because they don't have chips. Okay, so physical car is being already ready and it's there, but because they don't have the chips, okay, they cannot actually deliver the vehicle to the customers, right? So until and unless the chips and everything is installed into the car, you cannot sell it. So they were able to manufacture the car in a sense as a body, but not the computing or the network on the car, right? So that's the time we are in, and certainly computational fluid dynamics plays a key role in designing the car in terms of aerodynamics as well as safety and those parts are concerned. But at the same time, car itself has become, as I was saying, supercomputer on the wheels, right? You do huge amount of computational things on the vehicle itself. Okay, and even if you see today's vehicle, those are extremely sophisticated, and lot of the bill of material of the vehicle is based on the electronic component rather than the mechanical components. Okay, so that's where we are already going. Okay, so let's move to the next vehicle again from the aerodynamics point of view. Okay, probably soon we will have our own bullet train in our country, but this is in, I think, Japan or China. I'm not sure. But if you want to run train at such massive speed, you cannot have the engines that we typically have it in India, right? So that shape, okay, apart from the engine power, okay, the shape of the engine itself will have a lot of air resistance, right? To minimize the air resistance, you need to design the your train something like this, right? So this also involves a lot of computational simulations and so on. Okay, especially the computational fluid dynamics. So what kind of computational fluid dynamics we do? Okay, so this is a very simple chart one of my lab mate did. Okay, so you see there is this formula car. Okay, when you have these cars running at really high speed on those race tracks, okay, actually people see what kind of drag different components of that vehicle exert, and you can actually see the streamlines of this vehicle simulation. This is the screenshot of actual simulation of formula car. Okay, so you can see certain areas there will be, so for example, this part, this part, this part, so there will be a lot of resistance, whereas if you look at this part, it's smoothened out, and it makes easy for the air to just slide over it. And probably many of you might know this tail here is essentially to stabilize the vehicle, okay, so that it will not jump around and so on, right? So those kind of features are added and then simulated, and then based on that simulation results, actual vehicle will be modified or manufactured. Okay, without this kind of simulations, you cannot actually have this vehicle manufactured. Otherwise, you'll have to do n number of different prototypes before you get to the final prototype, right? Yeah. So another classic example that probably everybody must have seen this this kind of scene when we are any guess whether we are taking off or landing here? Anyone? So I believe everybody is favorite seat is the window seat when we are flying anywhere, So any guess whether the aircraft is taking off or landing? So obviously it's not in at 35,000 feet. Either it's taking off or it's landing. Any guess? Okay, so probably next time you can actually go and see, like, this is landing. Okay, so what it's trying to do is it's trying to increase the drag over the, your wing. So these are, things that define how the airflow will move over your wing, right? So this is when you are actually cruising. Okay, this is where you are taking off, right? This is when, you want to just, take up. Okay, and this is that image that we saw in the previous slide. This is where, we are trying to increase the drag so that, our aircraft will slow down, because, you are landing, right? So these kind of simulations people have to do before, so for example, you must have seen like recent events with especially Boeing. Okay, there were few accidents, okay, because of some software glitch, certainly. But they tried to solve simulation or aerodynamic problem by adding some flaps or something. I don't know the exact name. Okay, and because of that, it was unstable, so they added a piece of software, okay, to control it. But because of some bug in that software, it nosedived the aircraft a couple of times. So that was a key reason behind those accidents. But point is, it's all physics, and this is all you can do it on computers. You don't need have to actually build the aircraft, fly it, and actually operate it to see whether it works or not. Okay, you can do all those things in actual simulations. Okay. Okay, so I'll just briefly talk about one of the interesting problem which I personally worked on. Okay, so we had one project with ISRO, and ma'am mentioned it in my introduction. So this was phase one of that particular project, where we took their code, parallelized, optimized it, and delivered it on the GPUs. Okay, so what you see here is a propulsion system. This is a nozzle of a rocket. Okay, in 2D. So this is the symmetry line. So if you so this is a axis symmetric problem. So if you take this particular area and just run it across around this symmetry, you get a 3D shape, right? Because this is axis symmetry problem, you don't have to solve it as a 3D. You can solve it as a 2D, and whatever simulation results you get for 2D, you can just extend it to the 3D, and it will work. So this is the axis of symmetry, and you just have to rotate it by 360 degrees, so that you get the full picture. Okay, so the thing is, there is this group in ISRO which actually analyzes all these rocket designs for different groups in ISRO. So let's say you are some group in some XYZ ISRO lab, and you are trying to build a rocket for certain mission. Okay, so before actually you go and build the prototypes and all, you have to submit the designs to this team. They will run the simulations, and based on the simulation, they will give you a report saying that what is the thrust that you can get, and what is the good part about this thing, what are the negative points, if any, and so on, right? And based on that, you can modify the design, or you can continue the same based on the report, of course. Okay, but before you actually go and do the prototype, okay, you have to do a simulation, and then this group will give you a report, right? And that code we took and parallelized, optimized it on a GPU, right? And phase two we did it for newer generation of GPUs and so on. So point here is, it doesn't really matter whether you are in US or in India. We use these tools day in, day out. Okay, and without these computational tools, you cannot actually build anything in finite amount of time, right? In that scenario, what will happen is your codes will take or your project itself will take years and years just to build the prototype, test it again, based on learning, go back to the drawing board, modify it, build a prototype, and so on. So that's why you need a computational methods to do the simulation virtually, and you can do hundreds of different simulations provided you have that much computational power, certainly, in parallel, and you can evaluate multiple different designs, and based on the feedback you can choose the best designs, and you can actually just prototype few of them and test them out instead of prototyping it for the each and every design that you initially conceptualized, right? So that's the advantage of these computational techniques. Okay. Okay, so now moving to slightly different industries. So every city, nowadays outside, you'll have places like MIDC and industrial areas which will have a lot of these chemical industries and so on, right? So what these industries typically have is they have these mixers, okay, which we here I'm trying to show you one such thing, where they'll add different chemicals, and after their reaction, you get some output, whatever you are trying to build product for, right? So when you do those kind of things, so I've just given you a simple example here. So you have this cylinder in which you have this agitator which rotates and mixes these different fluids, right? So you added let's say chemical A, chemical B, and you get a chemical C as a part of this reaction. But for the reaction to happen, if you just pour A and B, okay, unlike the experiments we did in labs during our college days, right? So we'll put A and B and we'll shake it, right? So these are very large mixers. You cannot just check them. So what they do is they will have these agitators which will have this rod which will rotate, and it will have some arms and stuff like that, and which will try to mix the solution. Okay, so your final yield of let's say solution C or chemical C depends on how well amount of A and amount B was mixed. Okay, if it mixed 100%, then your yield will be 100%, but generally that won't be the case, right? So if you have a certain agitator, and if you have this system where your yields are let's say 70%, you can redesign some of these this part based on some simulations. Okay, and you can improve the yield. Essentially you can improve the mixing quality, right, based on certain designs, and probably it will cut down your mixing time or reaction time, or improve the yield or whatever. So you can have multiple objectives, but the idea here is we want to redesign this so that you get maximal benefit out of the same thing. Okay, so the idea here is you cannot design n number of different prototypes and do it, so you better do a simulation and then you do it. And if you look at today, a lot of the local industries actually hire some of these companies who will do this study for them and improve the yields. And it's not that, again, it's not that only advanced countries use it. We use it here in India, and there are so many companies actually specialize in giving this kind of services, where you as a chemical industry, you can just approach them and with the designs, and they will give you a modified design based on your specification and all, and you will find some better results with the same thing, right? So that's the idea here. And it's been, as I was saying, it's been used over a period of time. It's not people have just started. People have been using it for quite some time now. Okay, so this is happening in real life. And if you have friends in probably chemical engineering department, now probably they are the better people to explain this to you, right? Okay. So okay, so another interesting project, I'm interacting with one of the researcher with this project. That's why I highlighted this thing here. Okay, so you must have seen a lot of these wind farms coming, especially in Sahyadri region, right? And in US, there are states which are very windy, as in you can install large wind farms, unlike in our area, probably wind turbines you see on the top of certain mountain ranges and all. Okay, there you can find it on normal plains also, because there's a lot of wind and so on. Okay, so what we are seeing here is let's say you are a large operator and you have a large number of such turbines. Okay, so for example, this is example where within a 10 kilometer cross 10 kilometer, you are installed 20 turbines. So this dot represents the turbines. Okay, and now you want to find out how much energy I can generate out of this turbine. So what kind of electricity output I can have by installing it like this or with different shapes and form, provided I have some data about like what kind of winds I get. Okay, so for example, if you can see here, when this turbine at the front, or like you can see here, when this guy which is at the front, which is taking the input air, okay, it's generating some electricity here, but still that wind is flowing to the next guy. So this is the top view, which is easy to follow, right? You can see that there is some wake of this particular turbine which is affecting the output of this guy. So if you put them in this sequence and this is how the direction of my air is flowing, probably the output of these guys will be much lower. Okay, so instead if you put them in some kind of a zigzag manner or some alternate manner, probably their output may increase, simply because now you are tapping only the air on this particular line or this particular line on this particular line, but there are some gaps in between where you are not tapping the energy of that particular air which is passing through, right? So there is this project called a Exawind project, which actually it's a coupled model which does like a lot of the things. But idea here is when I have a large scale wind farms, okay, how do I place the like wind turbines in a such a manner that they are not going to affect each other's performance significantly? Certainly there will be some effects, okay, because of the turbulence, but we want to minimize the same, right? So idea here is to optimize the overall electricity generation, because the investment is going to be same. uh,
Participants, kindly mute yourself. Participants,
yeah, sorry. So what happens here is it's going to actually cost you the same amount of money, but because the way you have placed them, okay, your overall electricity generation will be very less, right? And this is a very complex simulation to run. So that's why if you look at the name of this software tool itself, it says examine the exascale. So probably other speakers might have already talked about the exascale and all those things, right? So you need the very high computational power to run this kind of simulation, and this is a very important application for large scale such plants, especially when we are talking about building renewable power into our actual power mix. And we want to have a significant power coming out of solar, wind, and other renewable sources, right? So large scale installations certainly are very much interested in figuring this out. Yeah, and that's why this is the code, and in fact the code is open source, so you can actually go and take a look at it. Okay, only thing is you need a very large machine to run. Okay, certainly some smart test cases will be there, but yeah, and it's a very interesting problem to work on. Okay, so if somebody is interested, we can talk about it during the question answer session. Okay, so another interesting problem. Okay, because I showed the other day, on Monday, I showed one of the simulation where the lunar lander was landing on, moon or whatever, the lander is landing, right? So there, you have, so when it's entering into the atmosphere, okay, we call it as a re-entry or whatever, right? So for example, it's called as re-entry because it goes out of the atmosphere and comes back into the atmosphere. So for example, you must have seen this new developments with ISRO. So they want to send person to outer space and bring him back. So probably everybody remembers the Kalpana Chawla's episode, right? So when they try to enter into the atmosphere, because of the friction, the temperature was too high, and they had an accident. Okay, so when you re-enter into the atmosphere, okay, whether it's whether it's earth or no any other atmosphere for that matter, okay, there is a lot of friction involved. And you are actually at a place where the atmosphere is not very dense as it is there on the surface, right? So it's rarefied, atmosphere where the air molecules are very much rarefied. So the kind of numerical methods you want to apply to simulate this thing is very different than what you do when you actually do a simulation like this. Okay, so here the numerical methods that you use are very different than the numerical methods that you use here, right? So when this vehicle re-enters into the atmosphere, okay, there will be a lot of friction, and these surfaces will heat up, and in fact, this particular part, which will have like really high temperature. In fact, this is one of the, I think is ICBM, intercontinental ballistic missiles, front head, or they call it as a multiple warheads or something like that. So it's one of the, it's not actual thing, but it's specifically for um, targeting the warheads and so on. But nevertheless, this frontal part or this particular thing is going to re-enter into the atmosphere, and when it's re-entering into the atmosphere, okay, things are very different. Okay, so it will have a lot of friction. So how do you design it? Okay, again, you cannot experiment and collect the data, and based on the physical experiments you can modify this thing. Okay, so in early days that's what people used to do it, but now we have computational power available. Okay, and you can actually take this and simulate it, and based on that, you can keep revising the designs, and you can come up with a really interesting designs. Okay, so again, simulations are used here for figuring out the designs and the coating and the material to be used, and uh, weight and everything, essentially, right? So again, HPC is something which comes into the play here, right? So that's how probably you can quickly figure it out, right? Okay, so finally, towards the end, I just wanted to show you a nice simulation of one of this thing. Okay, so how do we actually do it? Okay, so how do we use HPC for such problems? So this is a one simple rising thermal bubble problem where, in this is one of the atmospheric sciences test case. Okay, so where there is a thermal bubble which goes upwards, and it will break like this, right? So that's the interesting bit about this simulation. Okay, but point is, the way we do is you take the mathematical formulation of the problem in hand. Okay, then you generally it will be defined as some kind of partial differential equation. Okay, you discretize that PDE. Okay, and okay, even though I said in initial state, okay, it can be initial value problem or boundary value problem. Okay, there are different variables, so that's why I said this is one example. Okay, so let's say I have an initial state. So for example, if I want to simulate the atmosphere, what I do is I have the mathematical formula for atmosphere modeling. Okay, what I do is I take the actual real-time values of temperature, pressure, humidity, and everything from the different stations, collection stations which I have. Okay, I now have an initial state of my atmosphere. Now I want to simulate it, and I want to forecast okay, what will be the situation tomorrow, day after tomorrow, or 1 week down the line, right? So you take the initial state, okay, and you move that current t is equal to 0 to t is equal to delta t. So whatever you have at whatever 7 p.m. in the evening today, okay, so now your step will be a couple of minutes. Okay, after a couple of minutes, what will be my situation? Okay, how the current state will evolve into the newer state. So step by step, you will take different time steps to evolve. Okay, so let's say minute by minute, minute by minute, minute by minute, you'll keep up evolving this simulation, unless you go to you finish 24 hours, 48 hours, or whatever your target is. And after 48 hours, or 1 week, whatever the simulation state you have, okay, now you will say that okay, now there is a lot of humidity or whatever, it will rain and things like that. Okay, based on that simulation, you will make some predictions, right? So that's how we use the computers to simulate these things. Okay, and without doing it in really large HPC machines. The key challenge here is because these are very complex large volume. One is you won't be able to fit it in single machine, but even if you are able to fit it in a single machine, okay, the amount of time it takes is huge, right? So if you, let's say, forecast tomorrow's weather and using a particular computer, but that simulation will take, let's say, 1 year, then it's like simulate forecasting tomorrow's weather 1 year later, which is useless, right? If I want to forecast for tomorrow's weather, then I should be able to do it in couple of hours so that I can disseminate that information with the public, right? If I want to forecast for a later date, okay, I should be able to finish it before that date. Otherwise, it's useless, right? So that's where HPC comes into the play, and you need like massive machines. So in fact, if you are following the news, okay, recently we have installed a new supercomputer here in Pune, okay, which is the largest supercomputer today, okay, which has the computational power in not in top 100 supercomputers, but as compared to our country, it's massive. And in fact, they installed two, one here which is a larger machine, and one in Delhi which is slightly smaller than this machine, and combined these two machines, probably I think government paid about 800 crore rupees for just buying this machine, right? That's massive investment which goes into building such machines. Okay, certainly if tomorrow like government says I'm ready to put in 10 times more money, probably you'll get like 10 times bigger machine, and probably our accuracy will also increase. But it comes at the cost, right? So that's where you have to balance and so on. But point being, it's not a very simple problem just to take a code and parallelize and run. Okay, scaling these codes on really large machines come with its own challenges. Okay, so, okay, I'll just move on to the very first slide where I started. Okay, so there are so many different areas where we can do this HPC simulations, and actually, when we talk about this list of supercomputers across the world, which are and people claim countries claim we have the fastest supercomputer in the world and so on. But trust me, there are so many private organizations or even some government organizations who don't really share the information about what kind of larger machines they have, right? So whatever we know, which is in public domain, but there are so many machines which are not even public domain. There are some machines which are in we know that they have it, but we don't know what exactly they are using it for, right? So a lot of the machines are being in US, the in fact the largest supercomputer today will be used for simulating the nuclear stockpile that US has, right? So they nowadays everybody knows, right? You cannot have a nuclear explosion for the experimentation, right? So what they do is they simulate these things on a supercomputer, and accordingly they improve their nuclear weapons and so on and so forth, right? So there is massive amount of computational power available across the world, okay, and people use it for all kind of crazy things. Today, the most hyped uh, domain is AI, and Elon has recently got a new supercomputer which contains 1 lakh GPUs, which is probably itself is really large machine. But if you just go back a couple of years ago, there was a lot of crypto hype, right? When people bought GPUs like crazy, because people used to do crypto mining on GPUs, and there are large data centers specifically built for crypto mining. Okay, before that, if you just go probably some other application. Okay, so over the period of time, there will be some application which will be at the forefront, which is using the HPC resources or computational power like crazy. But you'll find that there are so many other areas which are already using this HPC for a lot of interesting problems. Another last example which I'll give is during the COVID, most of the large supercomputers which are publicly available, which are owned by governments, actually were devoted for COVID vaccine finding and simulating the COVID thing and so on, including ones which are available in India, right? So everybody kind of focused on one application. but certainly there are large number of applications people have been using. And in fact, if you see the today's large cloud service providers, they are in a sense large HPC machines, and in fact today you can actually run large HPC jobs on those cloud infrastructure also. So they provide some bare metal services also, okay, which will have lower overheads as compared to typical cloud instances. But still, if you go and take those things, those are again massive HPC machines on cloud environments, right? So it's been used rigorously. It's just that we may or may not be aware of these things. Okay, yeah. So I'll stop here. If there are some questions, I'll take. If not, there are some few points I can add more. But yeah, let's take questions. Okay.
Participant, you can ask the
Again. Okay, so somebody raised their hand. Ma'am, question?
ma'am, please unmute yourself and ask the questions.
Josna ma'am, Josna Chavan ma'am.
Okay, no problem. So, any other questions? Okay, so just wanted to add few points here. I couldn't cover that part, because I thought, there'll be a few questions. Okay, so if you look at, a lot of these, for example, medical imaging, field, there's huge amount of work being done, especially from drug discovery point of view, right? So all these companies, they cannot actually just go and try to look at each and every chemical composition to see if that particular thing can be used as a drug, right? So what they do is they might have thousands of different potential chemical compositions, and you want to cut it down to few, let's say 5 or 10, so that you can actually do clinical trials and so on. Okay, and nowadays people are using AI for this thing, so that they can drastically cut down the things. But ultimately the point is, I briefly mentioned about the COVID thing, right? So why somebody wants to simulate that particular virus, right? So the reason is, if we know how the virus works at the molecular level, okay, inside a cell, how it attaches to some RNA or mRNA or whatever. I'm not expert in that field, but if I know this is how the chain of sequence of operations happen inside the cell, okay, I can just go and break that chain. If I break that chain, okay, it will not replicate or whatever, it will break that particular thing, right? And that's my drug for that particular virus, right? So to find it out, you have to do the molecular dynamic simulation. So how mRNA goes and attaches to a certain point and so on. So what I can do is I can have a drug, okay, which looks similar like this, or can form similar bonds like that and so on. So instead of that mRNA going and attaching it to that virus molecule or whatever, it can attach to my drug molecule, so that chain is broken. Or somewhere I can just go and break certain chemical reaction, things like that. So for all these things, you need to run these large scale simulations at the atomic level, okay. And now we are talking about very complex molecules with all their bonds and everything. Yeah. This all pipeline has been optimized, modified, and run a number of times, so that you get a drug, okay, and then quickly you can get into clinical trials and so on. But the point is, there are a lot of interesting application domains where people have been using it. But unfortunately, as we been talking about the HPC, but we don't focus on training our students to use HPC models, especially the parallel programming. So we have been using multi-core chips for last like 15-20 years now, and still some of the universities don't have the parallel programming in their syllabus. So uh, being a computer science student, probably if they know a lot of these things, probably they can go and contribute a lot of this knowledge into a lot of these different domains. Especially if you see today, all these different domains, all the parallel codes written by people are those domain expert, and rarely people like me who will be working with the domain expert to parallel optimize the code. But we need large number of people who can actually go and write parallel codes. And especially in AI today, if you see, okay, if you just go and Google, there are large number of jobs available for students, certainly who can use the tools, but there are a large number of jobs available for somebody who can write low level code to optimize all these numerical linear algebra libraries, or all the LLMs on the new platforms, and so on and so forth, right? And at the same time, as I was saying, the quantum is also coming up, and once that becomes kind of mainstream, or at least a lot of people start using it, probably some new programming paradigms will come, and so on. But point is, these application domains where you need a computational power will remain as it is, and they continue to evolve as the newer and newer technologies are available. So today, anyway, we have been using HPC for quite some time now. Today AI is there, people are using AI to simulate computational fluid dynamics simulation much faster. Okay, so there is a HPC plus AI into this. Okay, so it cut down the computational time or computational efforts by 100 or 1,000 times, right? So in fact, if you just Google this NVIDIA and weather forecasting, or I think climate simulation or something. Okay, they are building their own model based on some AI into it, which will drastically cut down the computational cost, right? So we are already using AI for a lot of these computational things. There is another thing called as PIN, physics informed neural networks, where people are using the neural networks in conjunction with physics part. Okay, I'm not expert in that domain, but people are using those techniques to speed up their calculation. Then there is an interesting field where people are trying to use mixed precision. Okay, so everybody I think knows that these all these AI computations, nobody actually uses 64-bit precision. People are trying to use like 16, 8, or even 4-bit integers for doing all these computations, right? So now all the latest hardwares are actually coming up with low precision support, and a lot of these computational problems where every time you don't have to actually use 64-bit precision. Okay, probably sometimes with 32-bit also you can get similar accuracy, or sometimes 16-bit also you can get similar accuracy, or you can get a lower accuracy but you can do more number of steps and get to the same level of final results, right? So a lot of new domains are coming up because of the advancements in AI hardware. Okay, which is also affecting a lot of these application domains. And if you ask me, there are so many interesting research topics available. Okay, and especially I believe most of the participants here are faculty members from different engineering institutes. The good part is all the domain experts are are there with you. Okay, in your institute, probably mechanical engineering department, civil department, other departments. You have to just go and collaborate with them, and see how we can apply the computational expertise that you have, and the domain expertise that they have, and you can get really good certainly papers, projects, and even good startups out of this. Okay, so that's where I'll stop, and if there are some questions I'll take, or otherwise probably I'll give a couple of minutes to the next speaker.
Participants, unmute yourself and ask the questions. Josna ma'am.
Yeah, that's fine, mine. So probably let's give 5 minutes back to everyone so that they can have some bio break for 5 minutes or something. Yes, thank you. That's all from my side.
First and foremost, we extend our deepest gratitude to Mr. Mandar Gurav for gracing us with his presence and sharing his valuable insights. Your deep dive into how HPC is transforming industries through real world case studies has provided us with a clear understanding of its potential and impact. The examples you have shared have truly inspired us to think beyond the traditional applications and explore the innovative solutions. Thank you, sir. Thank you so much. Please accept our virtual token of appreciation. Thank you all.
Thank you, sir.
Participants,